Okay. Hey everyone, welcome to the talk on a practical guide to singular value decomposition in Python. Please welcome Daniel, who is an organizer for PyBay, a regional Python conference in Bay Area. All right.
Hello, thank you for coming. So today I want to cover two main things. First of all, I want to cover what is SVD, most importantly in the context of recommendations. And then the second thing is obviously, how can we do SVD using Python? But before we start, let me ask you two questions. Have you ever wondered why you binge watch Netflix? Or maybe, how did Spotify find out that secret love for Taylor Swift? In fact, there is something about these services, such as Spotify, such as Netflix, that make them so intimate and so personal. Why is that? The answer is recommendations. Let me tell you why I'm here. So I work for an online dating company called Coffee Meets Bagel. Who knows Coffee Meets Bagel? Hey, right, brilliant. Okay, hope you haven't had bad experiences. It's a great dating app. And I recently moved from a traditional software engineering role to a machine learning engineering role. And most importantly, I did so with very, very little scientific background. And I know what you're thinking, that's a terrible idea. But today, what I want to tell you is, what I want to show is how Python really helped me learn and get up to speed with some of the learning algorithms that we run at Coffee Meets Bagel. Most importantly, some of these algorithms are a lot more easier and logical to understand when you're looking at Python source code, when they're implemented in Python. And today I want to show you an example of one of these. So before we start, I just want to make sure we're on the same page. What is a recommendation engine? Many of you that probably have not heard of recommendation engines have probably heard of search engines. And search engines are, just think of these as like black boxes where you insert some parameters and you get some search results. Recommendation engines are similar to search engines, but they're personalized. It's just like having one search engine for every user in your application. What are the benefits of search engines? Well, because they're personalized for every user in your application, they give more personal results. They give those intimate results that we were speaking about previously. But most importantly, they learn over time. As your user explores the application, as your user interacts with the items, the resources that you have in your application, our recommendation engine will learn. And it will give better results. Again, there are many benefits. I just want to point out two. The first one is engagement. So there's a huge increase in engagement if you use a recommendation engine compared to a traditional search engine. And then the second one is also diversity of recommendations. So if your user is treated personally in your application, there also is a lot more sort of engagement and diversity in the results that user gets. And if that wasn't enough, let's look at some stats. 35% of Amazon's revenue is actually generated by some level of recommendation engines. And Netflix has over 75% of movies that are actually based on the recommendations. This is really huge. And so today, what I want to do is I want to cover only a specific subset of what a recommendation engine is. Effectively, it's a really big topic. It's huge. And what I want to talk about is a common strategy to perform recommendations, which is called collaborative filtering. In order to understand collaborative filtering, we need to first focus on the three main ingredients that compose collaborative filtering: users, ratings, and products. The users are effectively the actors in your system. They rate products. And you can think of the users as the readers of your blog, the customers of your online grocery store. Effectively, most of us assume we assume to be a user in some application. Users rate products, which are the far right of this slide. And the products are, again, very domain specific. They could be, in case of maybe Spotify, they could be songs. Or in Netflix, maybe they could be movies. Now, ratings are the glue that connect the users and the products. Effectively, just think of the rating as a number to somehow quantify how good an interaction was between a user and a product. And this number can be as granular as saying 4 out of 5, or it can be as simple as saying thumbs up or thumbs down, right? It's up to you as a developer. Now, for the simplicity of these slides, I'm only going to be focusing on movies as products. So from now on, we're only going to be speaking about movies. But remember, products can be whatever you want. And so let's try and answer this question. What is collaborative filtering? So effectively, collaborative filtering is a way to provide recommendations by leveraging the existing ratings of the users that are similar to you. And probably the best way to understand it is with this matrix here on the right. This is a user to movie matrix. Every row here is a unique user. And every column here is a unique movie. And the cell between a user and a movie identifies the rating that that user gave to that movie. And so as you can see here, there are two main ratings. Thumbs up means purchase the movie, and thumbs down maybe means like, give the movie back or something, or dislike the movie. This is our mini Netflix, right? We only have 5 users and 4 movies, so it's a very limited catalog. And so let's say our user 5 here logs into our mini Netflix, and the mini Netflix asks our collaborative filtering engine, can you provide a recommendation for the blue movie? Well, how do we do that? The first step in collaborative filtering is finding users similar to our user 5 here that have also rated that blue movie. Let's look at an example. So user 2 and user 5 both rated positively the green movie and rated negatively the red movie, the orange movie. User 3 and user 5 both rated positively the red movie and also rated positively the green movie. Most importantly, both user 2 and user 3 have also rated the blue movie, which is what we're trying to predict. So let me ask, any brave soul want to answer this question? What will user 5 think about the blue movie? Boo. All right. Fantastic. Yes, that's correct. So as you can see, we leveraged existing users' information to generate this recommendation, right? We collaboratively found the answer. And so, again, I want to go one step down the funnel. There are many different ways to provide collaborative filtering. Today, I'm going to focus on one specific: singular value decomposition. It's one of the most well-known algorithms in industry today for providing collaborative filtering. It's highly adopted in industry. It's actually used by many companies. People like companies like Spotify have also written about their implementation, and it's very, very scalable, actually. And just to show you how widely this algorithm is used, this is a picture from the Netflix prize. So the Netflix prize is this competition that was created by Netflix in 2009. It's an open competition that basically called all engineers and researchers around the world to compete to somehow try and increase Netflix's recommendation engine. Well, the winner of this competition, which are these people over here, actually won using variants of the SVD algorithm to increase Netflix's accuracy by 10%. That's huge. And just to show you the prize, these people got $1 million using SVD. So, listen to this talk. Listen to this talk. All right. So, hopefully by now, I've tried to convince you that SVD is a cool thing. But in order to understand how SVD actually works, right, the most important things, I want to explain to you how SVD actually predicts these new recommendations. Effectively, SVD is an algorithm that creates these things called latent features for every user and every movie in our ratings database. But in order to understand what latent features are, let's first understand what features are, just to make sure. So features in the context of machine learning are the metadata that we as scientists or engineers attribute or associate to our users and our products. So, for example, in the context of Netflix, what would be the attributes that we would associate to our user? Maybe their age, the region they're in, or their gender. And what about the movies? Well, the release date maybe, the director somehow matters, the duration of the movie. These are all really informative features for us as humans. In fact, we assume that the rating that maybe this user gives to this beautiful green movie is somehow impacted by these features that we define, right? Probably the best way to understand this is if you got like past ratings of maybe IMDb or something like that, and you actually you could actually use these features to generate some statistics, like maybe males in their 20s are rate higher Wes Anderson movies than males in their 40s, something like this, right? Statistically. And so what we do is we generate these features so that then we can feed them in some kind of learning algorithm that somehow identifies the importance or the weight of every one of these features. But again, there's one fault here, which is these features are generated by us as humans. And as humans, we can only define features that are somehow directly observable, things that we assume are important. But most of the times, there's a set of features that is not directly observable, but is a lot more impactful in predicting a rating. In fact, there's a class of algorithms, like SVD, that create out of nothing these new features, which we call latent features, just like age, region, and gender, that are somehow not directly observable. We can't point out saying the first latent feature identifies, I don't know, the users that have blonde eyes or something like this. We cannot do that. But all we know is that these features can be used and are highly informative in the context of recommendations, in predicting a rating between a user and a movie. And so SVD, as an algorithm, runs on these data sets and generates these features. And what do these features look like? Sorry about the picture, but they're very ambiguous. There's no way to actually describe them, and this is my creativity in trying to describe the features. They're not really something that you can actually point out. These are very abstract. But again, we can use these features in our data sets. So now let's try to actually understand how can we use these latent features. How are these features actually generated? Let's start from there. So again, let's take our mini Netflix example before. This is a mini Netflix, and even smaller, right? We used to have other 2 users, well, they churned. So now we have only 3 users and 4 movies. Most important, as you can see here, I'm not using thumbs up and thumbs down anymore. I'm actually using a number. Remember, the higher the rating, the more relevant. So for example here, user 2 rated very highly the red movie here, but rated very poorly the blue movie, because 4 is obviously bigger than 1. Now, let's just put this matrix over here 1 second. So it turns out that there is this algorithm, which is called matrix factorization, this technique. What matrix factorization does is it gets one big matrix, and it creates 2 smaller matrices out of this big matrix, in a way in which we could take those 2 matrices that we create, and in a second moment, we could recompose the original matrix. It's a bit hard to understand, but let's try to visualize it, okay? SVD is an implementation, an algorithm that uses matrix factorization, so decomposes these 2 matrices, in a way in which we only retain the most informative features, the most informative factors from these 2 matrices, the ones that have biggest importance. And the number of features that we actually extract is something that us, as developers or scientists, define. We tell SVD how many features we want from this data set. So let's say we wanted to run SVD on this matrix here, and we only wanted to output 2 features. What would this look like? As you can see here, we have every user has these 2 latent features here, and every movie has 2 latent features. And if you somehow believe me, you could get these two matrices and remultiply them together, and you would get an approximation, the nearest approximation to that center matrix, minus the question marks, which basically means that you can actually generate new predictions. Now, what about these features? Why are they? I only use 2 latent features here, simply for illustration purpose. But in your real example, you'll probably want to use more than those. The more latent features you generate, the more information you're actually extracting from the original matrix. The more latent features you extract, the more computationally expensive your SVD is going to take. So that is a number that you are going to describe. So now we have these latent features. What can we do with them? Well, today I want to show 2 use cases of how we can use these latent features. The first one is to predict new scores. Effectively, once we generate these latent features, we can predict the rating between any combination of user and movie. So let's take an example here. Let's say we had our user 1, and we wanted to predict what user 1 would think about the blue movie. So we just perform a dot product between the latent features of user 1 and the latent features of the blue movie. So we multiply latent feature 1 of user 1 with latent feature 1 of blue movie, and then we sum latent feature 2 of user 1 with latent feature 2 of blue movie. Result here is 3.52. So effectively, user 1 would pretty much enjoy the blue movie based on this example. And let's look at another way in which we can actually use these vectors. And this is the way I actually like most, which is effectively, once we generate these latent features, we could compare users with other users and movies with other movies. We could actually find similarity, the similarity between 2 users or 2 movies, by identifying the similarity of their vectors. And there are many different ways to measure similarity. Today I'm going to be using cosine similarity, which effectively measures the angle, the cosine of the angle between these 2 vectors. And so, in this example, you could probably say that if user free here is more closer in terms of tastes to user 1, is more similar to user 1 than user free to user 2. What that effectively means is that user free is more likely to agree with the tastes, the ratings of user 1 than user 2. And so, hopefully this is a bit fun, but what I want to show you now is a small demo. Effectively, what we're going to do is we are going to be training an SVD using a library called Surprise SVD. It's a really great library, and it's very, very simple to use. And what we are going to be doing is we're going to be downloading and exploring this data set, which is called MovieLens. And once we've explored this data set, we are going to train an SVD using very, very few steps. You're going to go back home today, and you can do this on your own data set. And then finally, those 2 ways that I was showing you before, generating recommendations by reconstructing the result, by performing the dot product between a user and a movie, and similarity between movies, we're actually going to be able to do that using this example. So, let's start by speaking about MovieLens. So MovieLens is a great open source data set. It's pretty famous. It's used in a lot of competitions. And it has a lot of different ratings and a lot of unique movies and users. I built a small function here called load MovieLens that simply converts the CSV file to a data frame, a pandas data frame. And as you can see here, every row is a past rating, right? And so, for example, if you take the first row, this user 742 rated Jeremy Maguire with a rating of 4. And again, the ratings go in scale from 1 to 5 inclusive. As you can see here, there are 3 columns to this data frame. The first column is a user ID. The second column is the movie title. And these are strings. They can be whatever you want. Your users and your items and your items and your product can be whatever data structure you want. The important thing is that the rating is a number, right? Remember, it needs to be quantifiable. So, how can we train an SVD using 4 simple steps? The first step is we obviously import surprise SVD, and we define something called a reader. And a reader is effectively a component inside of, it's a class inside of surprise that defines the lower and upper bounds of your ratings. Remember, you can choose whatever lower and upper bound you want. The important thing is that you define it up front and you tell surprise. So in this case, MovieLens has a great open source documentation which tells us that the ratings go from 1 to 5. So this is what I'm going to define. Second step is we initialize a dataset instance. And just think of the dataset as a loader, right? Effectively what it does is it prepares the data for performing SVD. Dataset accepts 2 parameters. The first one is the MovieLens dataset, the MovieLens data frame that we defined previously. And remember, this needs to be a pandas data frame which has 3 columns in this specific order: user ID, product ID, and rating. It's very important. And then the second parameter is that reader. Now, as a third step, what we want to do is we want to retain some amount of the data set for testing purposes later. Today, I'm actually not going to show you how to perform the testing. But if you download my notebook, you'll actually find some hidden slides that perform that. Finally, the moment we've all been waiting for is we initialize a new SVD instance, and we fit our data set. And here, as you can see, the SVD accepts 1 argument in its constructor, which is number of factors. This is the number of latent features we want to use. Remember, here I chose 100 as an arbitrary number. It just worked well with my examples. But you can choose whatever number you want, whatever number you feel confident. With the data set that I've been using, with the MovieLens data set, if you just take the good subset, for example, in this example you will be using, it will take very, very little to train. It's not a computationally, it's not a very expensive in this example. So, once we've trained that SVD instance, remember what happens. The SVD creates those 2 matrices, the user matrix and the movie matrix, right? And every one of these matrices has all these latent features. So where are these matrices now? Well, it turns out that there's this attribute called QI on top of the model that gets created once the SVD is run. And as you can see, this model has 596 rows and 100 columns. So why is that? Well, there are 596 unique movies in our ratings, and every movie will now have these 100 latent features. So now you may be asking, you maybe want to ask, well, sorry, something weird has happened. Oh, okay. So we have all these latent features, but how do we map every vector back to its movie? Well, it turns out that there's this hidden attribute, which is called raw to inner ID items, which is a dictionary. And this dictionary effectively maps every item, every movie in the way we defined it, in this case is a string, to the row index that corresponds to the row index of the latent features. So let's take an example. Let's say we wanted to identify Toy Story. The first thing that we do is we find the row index of Toy Story by using the name. And then once we have that row index, we can actually find all the latent features by indexing the QI matrix at that particular row. You're going to get the entire row back, and that's going to be 100 latent features in this example. So now we've learned how to train an SVD, and we've learned how to identify where these latent features actually are hidden. So it's time to show you 2 great examples. The first one is predicting a new rating between any combination of user and movie. This is very, very simple. As a refresher, this is what our MovieLens data frame looks like. Our user IDs are defined as strings here, so user 437, and movie title here also defined as strings. So Surprise SVD makes it really simple. There is a predict API, and this predict API accepts 2 parameters, the user and the movie. And the output here is going to be a prediction object, which will give you this, inside the prediction object, you'll have this EST attribute, which will effectively tell you the predicted rating. In this case, EST is 4, which means pretty high, right? So, I mean, everyone loves Toy Story, but this user in particular. Now, the moment we've all been waiting for. Recommendations by comparing items. This, in my opinion, is the most fun part. So, remember, as a refresher, two movies, two products are similar when the cosine distance is as near to 0 as possible. So, what we're going to do here is we're going to fetch vectors for 3 movies. The first one is the original Star Wars. The second one is Return of the Jedi. And the third one is Aladdin. First, I'm going to measure the distance between the Star Wars vector and the Return of the Jedi vector. As you can see, the distance is 0.26. Oh, sorry, 0.29. And let's say I wanted to perform the same distance between Star Wars and Aladdin. Well, our distance here is 0.85. So effectively, what that means is that Star Wars, the original Star Wars, is a lot more similar to Return of the Jedi than Star Wars to Aladdin. And remember, these were generated without any information, any metadata of the original features. There was no concept of a director. There was no concept of a genre, nothing. Just through the ratings. So now, what if we wanted to find similar movies by performing ranking, right? Effectively, what we could do is we could build one small function which would accept a movie title, and it would generate the similarity between that movie title and all the other movies in our system, and then rank those movies by similarity. What would this look like? Let's say I wanted to generate similarities for Star Wars. First result, obviously Star Wars, because it's itself. Empire Strikes Back, Return of the Jedi, Raiders of the Lost Ark. These are shockingly accurate. And remember, there was no information at all about potentially the same director or the same saga or any of that. Let's look at Pulp Fiction. Okay, Ed Wood, Train Spotting, From Dusk Till Dawn. And so what effectively this also turns out in a concept of rating is maybe you have users that enjoyed Pulp Fiction, and if they enjoyed Pulp Fiction, well, why don't you see one of these movies? Because they are shockingly similar and people rate them in the same way. So this is also another way of providing recommendations to your users. So in conclusion, SVDs are a really powerful technique to provide those recommendations. Once you generate these latent features, you can use them in so many ways. You can even use them as features for your classification algorithms after. And most importantly, if you want to get into SVD but you do not have a scientific background, really try some of these libraries, because Python makes the barrier of entry so low for you, and you can really learn as an engineer how these things actually work. That's all. Thank you very much.
Hey, if you guys have questions, there's a mic up front. We can probably take 3.
Hi, I was wondering how resilient SVD is against the curse of dimensionality.
Yes, that's correct. So yeah, I did try. I wanted to cover Pearson in this example, but I found cosine similarity just a very, very simple and more visual way to actually show this difference. But yeah, you could use you could also use Pearson.
So I was wondering, if you're launching a new product and you basically have a very poorly populated sparse matrix, like at what point do you get where the training of the SVD becomes actually feasible, right? Like if in your example of the 3x4, you only have 2 ratings,
Yeah.
then it's not going to be that helpful.
Yeah, that's a great question. So SVD is luckily a very parallelizable algorithm. And in fact, there are different implementations of this concept of matrix factorization. One of them is called ALS, alternate least squares, which has really great parallel implementations. One of them is actually present in PySpark, and it's also one of them that we actually use in production at Coffee Meets Bagel. And although we have found that SVD is more accurate under some aspects, ALS is a very parallelizable algorithm that will also work at scale. Did I answer your question?
So are you basically saying that if in the 3x4 you had only 2 of those squares populated,
Yeah.
ALS will be a better algorithm than SVD?
Oh, no. So I just said that as your data, so sorry, is your question like the more latent features you generate, the more computation?
No, I'm saying what happens if you want to train your SVD in that 3x4 and you only have 2 things that are populated?
Oh, yeah, of course. Good question. So it's still going to work, but the results are going to be really bad. So what you want to do is you want to measure the reconstruction of that matrix as your error, right? So you can use like mean squared error or some other metric to actually find the error between the reconstruction of the original matrix with yours. So the more ratings you have, the more accurate it's going to be.
Actually, we are running out of time now. Let's just take the questions outside. Is that okay? All right, thank you all for coming, and thank you, Daniel.